even if for some time they can join and maybe learn something. So so why do we need to sort? We have a lot of data. Like sorting is generally needed when we are working with a lot of data. So sorting helps us arrange all that data in some meaningful order. So like uh, it's easier to find your clothes when they are uh, when one drawer has all the shirts and one drawer has all your trousers, right? But it becomes hard when you need to find some particular shirt from a heap of clothes. So that's why sorting comes into play. So sorting helps, it makes it easier to analyze the data, visualize and understand the data, and also it makes it easier to find something from the data, which Anushka will discuss later, about how it becomes easier to search when all your data is sorted. So every sorting algorithm has different types, different time and space complexity, and they are used depending on the data which is to be sorted. So depending on the size of data, or like depending on how much time we can spare or how much extra space we have, we can choose different sorting algorithms. So generally, space complexity, time complexity, and stability. These are the three terms which are related to a sorting algorithm. All right. So like we have already discussed about space and time complexity in previous sessions. So I don't think I need to like uh, tell about that again. But stability is a new term. So I'll discuss about that. So stability of a sorting algorithm. Now this is related to data when it has a lot of you can say equal values. So let's say you have I'll show an example over here. So okay, here, so you can see that I have this array over here. So this has 4 two times and then 3 2 1. So I have marked the two fours as 4a and 4b. All right, so this is a different 4 and this is a different 4. So this is an integer array and I need to sort this array now. So uh, like when we sort that array using different algorithms, we get different result. One is this one and the other is this one. So you can see that 4b comes here earlier and 4a comes here earlier. So like we get these two different results using two different sorting algorithms. All right, so so stability is basically a sorting algorithm is called stable if two keys or two items with equal value remain in the same order in the output array as they appear in the input array. All right, so can anybody tell me which one is sorted using a stable algorithm? I'll show the. Can anybody just type 3 or 4? Which one is sorted using a stable algorithm? Yep, exactly. So 4 is sorted using a stable algorithm because as you can see that 4a appears before in the input data, right? And in 4, you can see that in fourth array, 4a is earlier. And in this one, 4a is after 4b. So like 4 is sorted using a stable algorithm, right? So like some sorting algorithms are stable by nature. So some algorithms are designed such that you don't need to modify anything, but they will just give you the output in a like they are stable. So the order remains same, or what you can say as a relative order of the elements. But some sorting algorithms are not stable. So what you can do is you can make them stable by considering the position of each item. So when you start considering the position of each item along with some kind of comparison, like less than or greater than, like in whatever order you want to sort them, along with that, you start taking into consideration the position of elements. So that makes the algorithm stable. So any algorithm can be converted into a stable form. Now let's talk about selection sort first. So selection sort has a time complexity of O(n)². it has a space complexity of O1, so it doesn't use any extra space. So when you give an array to select to and you perform selection sort on that array, there is no extra space required, so that array is modified like within itself. So these type of algorithms are called in place sorting algorithms. Selection sort by itself is not stable. Okay, so this one, so you can see that this three is sorted using selection sort. So I'll show you how selection sort works basically. I'll tell you first. So uh, selection sort basically sorts the array in this manner that what it does is it starts at the first element and then it moves over the entire array one by one. And it like let's say I want to sort in ascending order. All right, so it will move through the entire array and find the minimum element, because in ascending order the smallest element will come first, right? So it will uh, select the first element, then move through the entire array and find the smallest element, and then it will perform a swap. All right, like uh, so it will perform a swap and then our result will be this one. So you can see that 4a and 1 has been swapped. All right, the order of remaining elements is same. So you can see that selection sort is not stable because the order is changed, and here the order is not changed. Okay, so selection sort is not stable. Now we have the first element at its correct position, right? So now what it will do is it will select the second element, and then it will go through the entire remaining array, which is the remaining unsorted array, because this part is sorted. So it will not check this one again. It will start checking from this part and forward, because that part is unsorted. So it will again find the smallest element and it will perform a swap. So you can see that after that our array becomes this, and it has 1 2 3 swap, then 4b 4a. This part is already sorted, so nothing will happen, and this will be our final output when we use selection sort. So like, is the working of selection sort clear, like how it's working? What is a stable algorithm, Amit? Like, is that clear now? Like, I explained what is a stable algorithm. Stable algorithm will basically maintain the relative order of elements, like using 4a and 4b. Yeah, cool. So selection sort has this thing. It's a like selection sort will start sorting the array from the first element. So as you can see in this example, uh, the in first step, the first element is at its correct position, and in second step the second element. Then in third step, if I take a bigger array, I can show a better example, or I can show a visualization as well, like if you all want. So I'll do a selection sort on this huge array. So you can see that what it's doing is that skip back. Okay. So I'll do a selection sort on this one. So you can see that uh, it's finding the minimum element. All right, you can see that it's finding the smallest element. This will be the smallest, and then it will swap 58 with 4 in first step. All right, so it's starting to sort the array from the first element. So if I speed that up, I'll show you in what order it is sorting. So you can see that the array is getting sorted starting from the first element, right? So I'll not show the entire because it's like you can understand from that how it's working. So and also another thing with selection sort is that it does not perform more than n operations on memory, because you can see that it's running over the entire array and performing just one swap with the smallest element and uh, the first unsorted element. So it's just performing n number of swaps at most. So that's one thing with selection sort. So uh, so this is a code sample. So this is a function that is performing selection sort on this array ARR, and the size of array is n. All right, so excuse the background noise. Okay. uh, so int I and j and pause. So what are these three variables? So I is the pointer, I is the position of this. So I step back. So in first step of the array, I is at 58 at this position. All right. Or I'll show on my board. Just a second. Yeah. So when the sorting begins, this position is I. Okay. And to iterate through the entire array, we use J. And after this iteration, POS will contain this, the smallest element. Right. Okay, anyway, like I think it's clear. I don't need to write. Right. Okay. So, uh, yeah, so I will be the first element with which we need to swap. Then J will iterate through the entire array, and POS will contain the position of the smallest edge found. So you can see that we are checking if ARR at J is smaller than ARR at position, then position equals to J. So basically we are finding the position of smallest element, and after this iteration is complete over the entire array, we are just swapping the two elements, swapping ARR I and ARR at POS. So, and as you can see that J is starting from I plus 1. So like in this one, you can see that when the sorting is happening, so after the first element is sorted, it doesn't check it again. You can see that it's not becoming red now because the array is starting from I plus 1. All right. So that's how selection sort works. So I think now you can understand why the time complexity is O(n) square, because in worst case it has to swap all the elements one by one, because you can also see that the outer loop is running uh, n times, and the inner loop is also running for a total of, like, for each iteration it's moving over the entire array. So acha, can anybody tell me what is the best case for any kind of sorting algorithm when the complexity becomes O(n)? Like when you are sorting something, so what can be the best case? No, I mean, like, if I give you an array and you want to sort it, yep. If the order is maintained, or we can say that if the array is already sorted. So if the array is already sorted, then that becomes the best case for a sorting algorithm. It doesn't need to do anything, right? And what can be the worst case? Can we tell? Like if I want to sort an array in ascending order, so what will be the worst case? Yeah, the array is in descending order. Yes. So in that case, this sorting algorithm has to swap every element, or like change every element. Okay. So I think selection sort is pretty much clear how the algorithm is working and in which order the elements are getting changed. Like just type a yes or no. So I'll try to explain again. Okay. So next is bubble sort. Hmm. So next is bubble sort. So bubble sort also has a time complexity of O(n) square, space complexity of O1. So the algorithm is working in place. However, bubble sort is a stable algorithm, and bubble sort will start sorting the array from the last element. Okay, so that is a difference between selection and bubble sort. So I'll pause this one and I'll show bubble sort on this array. All right. So if you see bubble sort, you can see that the last element is sorted, is in its position, as 95 is the last. You can see that sorting from the last, from the end of the array. right? So that is a difference between selection and bubble sort. And also bubble sort is stable. So I'll show you how bubble sort is working on this. How do I remove this? Okay. So bubble sort, what does bubble sort do is it basically starts at this position, and it continuously performs comparison between two consecutive elements. All right. So when it's starting, it will perform a comparison between 4A and 3. I'll just remove this 4A now because I think it's pretty much clear why I have written this. So I'll remove this. Okay. So it will perform a comparison between two consecutive elements. So it perform comparison between 4 and 3. And let's say I want to sort the array in ascending order. All right. So in a sorted array, 3 will come before 4, right? So what it will do is it will swap these two elements and bring them in order. So like it will be 3 here and then 4 here, and the remaining elements will remain in same order. Okay, so this will be the array at after first step. And then what it will do is it will move one step ahead and perform comparison between these two. So again, you can see that the order is not okay. So it will again like change the order. Okay, again, like it will swap these two elements. So it will basically become, yeah, it's 2 here and it will become 4 here. Okay, so now it will again move a step ahead and it will perform comparison. So you can see that these two are like equal. So it will remain them as it is. So you can see that since these two remain as it is, their order is also maintained, because this 4 was 4A, like this was 4A and this was 4B, and bubble sort is not swapping them. So they remain in same order. Then at last step, it will perform a check here, and I'll fix this array. So you can see that 4 and 1 are not in order. So it will again like perform a swap. And so it will be 3, 2, 4, 1, and a 4. Okay, so this is one iteration over the entire array of bubble sort. And this process will be repeated. So as you can see that after one iteration, I have my last element at place, which is 4B. Right, so 4B is at its place and 4A is still here, and like even after multiple iterations 4A will still remain before 4B. So this is first iteration and this will be repeated for as many elements as there. So and we will get our sorted array. So you can see in this visualizer too. I'll skip back and I'll show bubble sort again. I'll reduce the speed a bit. So here you can see that it's checking two consecutive elements and swapping them in order. Like if they are not in order, then they are getting swapped. But if they are already in order, it will do nothing. It will move ahead. And as you can see that the largest element is just moving behind, and we get this last element. So I'll speed this up a bit. So you can see, right? So this is how bubble sort is working. So if you can see that if two elements are already in order, uh, uh, okay, so I'll step back, or I need to find some. Okay, anyway. So I think the idea is clear that if two elements are, it will do nothing. So here you can see that these two, 58 and 58, like they are in order. Then 58 and 59 are also in order, so it will not do anything. It will just move ahead. Now it will swap 60 and 14. So this is how this bubble sort is working. All right, so I'll show a code. So this is the code for bubble sort. So I'm given an array ARR and the size is n. Now I and j are the only two values we need here. I will be the outer loop. So I will basically uh, count the total number of iterations, or I is the total number of iterations for the entire bubble sort to run. All right, and then j is basically the inner loop, and j is running here. You can see that something to pay attention is here, n minus I minus 1. So n minus I minus 1 basically prevents the algorithm to check these sorted elements again, because they are already in position, so we don't need to check them again. So as you can see that these sorted elements are not getting read again, because of this condition of n minus I minus 1. So the sorted elements are not getting checked again, just the unsorted array is being looped over. So as you can see that we need to sort it in ascending order. So if ARR at j is greater than ARR at j plus 1, which means that, okay, I'll show you here. So if ARR at j is greater than j plus 1, which is true in this case, so then we need to perform a swap, because the bigger element needs to go behind. So that's what this bubble sort is doing. All right, so it is just swapping these two. Okay, so can you all tell me if the algorithm is clear, bubble sort is clear, or something to explain again? Okay. So then we have insertion sort. So this one is generally not used, this algorithm. Uh, it has a time complexity of O(n) square, a space complexity of O(1) as well. It is a stable algorithm as well. This algorithm is generally used when number of elements in the array is small, or when the input array is almost sorted. So insertion sort is generally not used because it performs a lot of operations on memory. It performs more operations in memory than bubble and selection sort. So that's why we don't use insertion sort in general. Uh, so I'll, I'll show insertion sort here as well. So like okay, so I'll reduce the speed a bit and then play. So what it is doing is that it starts at any element, and it starts at an element, and then it keeps moving the element behind unless it is at its position. So it will keep shifting elements forward unless that element is in position. All right, so you can see that it's shifting all elements behind unless it's in position. So if I speed this up a bit, so you can see how, you can see that it's performing a lot of operations. However, one thing you must have noticed is that insertion sort repeatedly checks the sorted array as well. On square. Yeah, on square. Yeah. Acha, Anushka ne. Acha, okay. So you can see that in insertion sort, it's checking the sorted part of the array again and again instead of the unsorted part. So that's a difference between insertion sort and the selection and bubble sort. Selection and bubble sort don't check the sorted part once the element is in position. It doesn't check the sorted part again, but insertion sort will check the sorted part. So as you can see that the this you can this front part of the array is sorted. Still, it is performing comparisons on the uh, partially sorted part, right? So that's how insertion sort works. So insertion sort, I'll show with a code example. So insertion sort, we are having this array size n. Now we have three values here as well, I, j, and key. All right. So you can see that I is starting at 1. Okay, so it will start at this position 38, and what it does is that it start checking behind. Okay, so key has the value at arr I, then j is I minus 1. All right, so when I is 1, so j is 0. And then what it will do is that while j is positive and arr at j is greater than key, which is sorting in ascending order. So if, like, you can see that 58 is greater than 38, so what it will do is that it will move 58 ahead. Okay, it's moving 58 ahead. I'll show a step. Uh, mm, skip. How can I show a step? Okay, anyway. So I'll reduce the speed again. Okay, so you can see that it's starting at 38, then going one step behind, performing a comparison, moving 58 ahead, and then 38 is at its position. Okay, now it will move ahead. Now it will like move to 66, and then check 58 and 38 again. So like once it takes a value, it starts checking behind that and shifts all the elements which are greater than that value. So I want to sort in ascending order, so it will shift the larger elements ahead. Or if I want to sort in descending order, it will like shift all the smaller elements ahead. So that's what insertion sort does. So it's like shifting all the elements ahead. ARR at j plus 1 becomes ARR at j, then j moves one behind, and at last what it will do is it will place that initial value of arr at I, this initial value of arr at I, at its uh, position, right? When the element behind that is smaller, so it will place that value at that position. All right. So like like is insertion sort clear, like what it is doing and how it's working? It's basically similar to how we performed insertion in arrays. We insert an element and shift all the elements behind it forward. So that's what insertion sort is doing. These from the code sample ones. Okay, okay. So insertion sort, like we have this array ARR of size n. Now we have three values I, key, and j. Okay, so in this example here, key is basically okay. I'll show here as well. Uh, so okay, so what happening is that selection sort will, or I'll remove these. So what's happening is that insertion sort starts at this position 3. Now what it will do is it will move behind, check the array behind this 3. Now if 3, like if it finds any element which is larger than 3, so then it will like push this element ahead or shift this element ahead. So what it will do at next step, the array will become like this. So array will be this. Array will become this because 4 is getting shifted here because 4 is not at its position. However, we have a variable key. All right. So so basically we have a variable key which is storing this value of 3, which needs to be placed at correct position, right? So key is storing this value, and we are moving all the incorrect, like all the values at wrong position ahead. And then what it will do is when there is nothing more to check, so you can see that there is nothing more behind this 4. So what's happening is that it will place 3 at correct position. All right, so this will be the value uh, after the first iteration of insertion sort. All right, then then at next iteration, what it will do is it checked this place once. Now it will check this place. It will move to 2 now. Now it will start checking behind. Okay, now what it will do is that you can see that 2 should be at first position, right? So 3 and 4 need to be shifted. So what it will do is that uh, it will move 4 here. Okay, and then in next step, it will move 3 here. So this will be the array after that. So now you can see that there is nothing more left to check, and 3 and 4 have been shifted. Now it will place 2 at this position, right? So now the array will look like this. I should show here. So now the array will look like this. So you can see that this part is sorted, right? This part, if you see just this part, you can see that 2, 3, 4 are sorted. So similarly, it will work for the remaining array as well. So when this part is already sorted, so at this position, it will again shift all these elements ahead. It will shift all these elements ahead and then place 1 at this position. And then we finally get a sorted array. So that's what the code sample is doing. Like basically key is storing that value which needs to be placed at correct position. Then this while loop is shifting values ahead until it finds the correct position for this key. And then we are just placing key at its correct position and moving on to the next iteration. So like now is the code clear, like how the code is working? Yeah, cool. So yep, that's it. And here are some additional facts for related to sorting algorithms. So some other popular sorting algorithms are quick sort, merge sort, heap sort, radix sort, and sort. So we'll be discussing about quick sort and merge sort in upcoming sessions. So quick sort and merge sort basically take advantage. Uh, no, that's for searching. So basically quick sort and merge sort are faster algorithms for sorting. They work in logarithmic time. So like they use a concept called divide and conquer, which we'll be discussing ahead. So I'm not discussing about them now. And like many popular programming languages have some built-in sorting functions. If you have used Python, you already know about sort. Or in C as well, you can use the sort function to sort a vector or any kind of array or something. So C++ has a unique hybrid algorithm which is called intro sort, which uses multiple algorithms in synchronization, or what you can say is smart usage of different algorithms to sort quickly. Okay, Python uses timsort, which is again a hybrid algorithm in its sort and sorted implementation. So the built-in libraries are using multiple algorithms like in a smart way to sort any kind of data quickly. So that's it from my side, and thank you. And here are some of the resources. I have put this visualizer. You can go and check out this visualizer. You can also visualize other methods as well, like merge sort, quick sort, and shell sort. And yep, geeks for geeks. So that's it from my side. And now Anushka will tell you all about searching algorithms. So over to you.
Yeah, thanks, Evanshu. So my screen is visible, right?
Yep, it's visible.
Okay, so hi, I'm Anushka, and we'll be learning about searching algorithms here in this session. So, what are searching algorithms? What do we mean by searching algorithms? So, searching algorithms are nothing but just algorithms to find some kind of data within a given set of data. So, suppose you have a just a second. Okay. So suppose you are in a library and you are trying to find the book of Corman's book of Introduction to Algorithms. So what are you going to do? You are going to go to the section where the books related to computer science are there. And then you're going to go to the section where there are data structures and algorithms related books. So you are not going to go and check at the history section, right? You're not going to go and check at the physics section. So the way we are searching for a data within a given pile of data is depends on how we are storing the data. So so if you have stored the books in a pile of random books, so you will not, you will have to check each and every book there to find the book that you want, right? And if you are going to a library, you have those sorted. It's in an orderly fashion, so you can just go and search in a particular location and then get it, right? So it depends on how you're storing the data. For example, if you have an array, the way we are going to search for the data is going to be different from how we are going to search for an element inside a graph or maybe a tree. So it depends on how you are storing the data. And it just means that we are searching for some kind of data within some given set of data. So there are different type of searching algorithms like sequential search and interval search. Linear search falls under this sequential search, and for interval search we have something like binary search. Then we have jump search, interpolation search. There are a lot of searching algorithms that are used. But for our session, we are going to focus on the common algorithms that are mostly used, that is the linear search and binary search. So let's talk about linear search first. So it's the simplest kind of search that you can find. So it's just a very simple intuitive method. Like you are just going to check each and every one of the elements one by one. So suppose you have an array like this, and it's not sorted. So it's just random numbers and you're trying to find something out of here. So what are you going to do? The most intuitive method here is search one by one, right? Like if you're trying to find 12, if you are trying to find 12, you'll just start from 0, right? You're going to start from 0. You're going to see here and you're going to see that it's not 12. So you're going to move to the next index. So at 8, 12 is not there. So you move to the next index. At the second index, it's 7. So it's not 12. So you move to the next index. So you move one, you check each and every index one by one. So at 3, then you go to 4, then you go to 5, 6, 7. So at 7th index, you find 12. So at 7th index, you find 12. So you're looping through the whole array and checking each and every element one by one, right? So suppose something is at the end of this array. So you'll have to cross each and every element here to find it, go to it, right? So what is going to be the worst case time complexity for this? Can anyone tell me? So by worst case, I mean, if something is at the end of the list, like something that 75 is at the end of the list, I'll have to check each and every element first to find 75, right? So I'm going to check here at 4. 4 is not 75. It's not here. It's not here. So I'm going to check each and every element in the list. And when I reach 75, so I would have passed through every element here. So my worst case time complexity will be O of n. If I had to find something in the middle, after I find it, I am just going to break out of the loop, right? I have found it already. So the worst case is O of n. So I'll show you the algorithm first and then explain how I am doing it. I think it's here. So here I have just taken an array, an example for as an example, and I'm just printing it for reference, and then I'm just entering a key that I want to search here. So I have this array, and I want to find an element out of it. I'm calling it key. I'm calling it key, the thing that I'm about trying to find. So what I'm going to do, I'm going to go from the first index, that is the 0th index, to the last index. I'm going to the first index to the last index, that is 10. 9 here. So less than 10, so 9, from 0 to 9. And I'm checking each and every element. If array of I is equals to key, then I'm going to say that my index is I. At the I position, I found the number, and then I'm breaking out of the loop because I have already found the thing. Right. So is that clear? Like linear search, how it's working? Linear search. So it's just a simple method where we are checking each and every index, and whenever we are finding it, I'm just going to break out of the loop. And for worst case, I will have to scan the entire array. So in that case, worst case will be my O of n. So next is my binary search. So I have written the code here. I'll just send you the PPT later. So the next is binary search. So binary search is something that works only for sorted arrays. So only if your array is sorted. Like I said, uh, if you're in a library, the books are in an orderly fashion, right? So finding something becomes easier. So we can take advantage of the fact that that it's already organized for us. The data is already organized for us. So suppose you're trying to find a word in a dictionary. So the words are arranged alphabetically, like the words are arranged alphabetically, so finding a word becomes easier. So if it's in a novel where the words are scattered randomly, like there's no order for alphabetical order, so you cannot find a particular word there without checking each and every word in the book, right? But in case of a dictionary, the words are sorted in an alphabetical word order, and we are taking advantage of the fact, right? So in a dictionary, suppose you are trying to find the word tiger. Suppose you are trying to find the word tiger. So what do we generally do? We uh, pick a just we pick a random page, like we flip through a random page, and we probably not probably what I'm saying is that we flip through random pages, and maybe we got C. So words related, words starting from C are there in this page. So we're not going to check on the left side of the book anymore, right? Because we know that it's going to have words starting from B, A, and all. T is never going to come here. So if I get C here, so if I flip to a page where there is C, I'm never going to check the left side of my book, right? These pages, this side. So I'm going to flip this side of the pages, right? This side of the book. So we are going to try doing that until we find T. And then we are going to do that for I, G, E, R, right? So binary search is something similar. Like in binary search, we are doing something similar. In that case, we were just randomly uh, to some pages. But in this case, we are going to do it in a proper way where we are just dividing the array into half. Like suppose we have an array. Sorry for that. My pen is somewhat not working. So suppose we have an array. We are going to check at the middle of this array, and if we are taking advantage of the fact that the array is already sorted. So suppose in this array, I'm trying to find 4. I'm trying to find 4. So this is my key. So what I'm going to do is divide the array into half. So dividing means my middle element will be this one. My middle element will be this one. So if my middle element, my key is 4, my key is 4. So my key is smaller than 21, right? My key is smaller than 21. So I don't need to check this side because I know all the elements after 21 is going to be larger than 21 because the array is sorted. So I'm just discarding this entire part of the array. Like I do not need to check for after 21. So I'm now going to check only in this part of the array, only from -5 to 21. It can lie between index 0 to 7. So next I divide the into half again. So at 3, we are taking the floor value right now. Like this one is the middle element. Let's consider, okay. So this one is the middle element. So 4. So I find 4 here. So I found 4 in 2 iterations of the loop, right? Like first what I did, first I went to the middle element of the array, and then I discarded half of the array, and then I went to the middle element of my new subarray, that subarray that we did not discard, that we had. So I took 2 iterations. And if I had to search by linear search, I would have gone to index 0, that was -5. Then I would have gone to 1, index 1, that is 2. So we would have taken 4 iterations of the loop to find this one, right? So now suppose, let me find something else here. So let me try to find maybe 90. So what I am going to do is first again, going to the middle element. So the middle element is 21. So middle element 21, now my key is 90. So 21 is less than 90. So I know that the rest of the elements are also going to be less than 90, right? So it's in sorted order. I can never find 90 in this part of the array. So I'm discarding this half of the array. So this sub array is discarded now. So I'm not considering this part. So from 7 to index 14, from 7 to index 14, I'm going to check for 90 now. So this is my array now. I have discarded half of it. So here the middle element will be 56, right? So the middle element is here. So I'm checking here. So is 56 less than 90? Yes. So this part of the array is no longer needed because I know that 90 is greater than 56. So my 90 is greater than 56. So I'm never going to need to search this part of the array because 90 is greater than 56. So it will be after 56 in the sorted array. So next 11th and 14th. So my middle element will be, since I'm taking floor, so this one, right? So also from 75, it's 90 is greater than 75. So I'm again going to discard this part of the array. Now from 12 to 14. So the middle element is 90 and I found 90 here, right? So I took how many iterations of the loop I took? Like I divided the array once here, divided the array once here, once here, once here, and then again here. So I took 4 iterations, right? And if you had used linear search, you would have to check starting from 0th index. So you'd have found it at the 13th iteration of the loop, right? So this one is much faster because we are dividing the array into half and discarding half of it. So is it understandable? Like, what if the number of elements is 14? Uh, so in this one, okay, so I don't have a fresh copy of this. So, okay. So the number of elements is 14. So my array is this much, this long, right? So my array is this long. Let's not consider 100. So number of elements is 14 now. And I want to find 90. So let's try to find 90 here. So I'm first going to the middle element First going to the middle element, that is 21. My key is again 90. So 21 is less than 90. So I do not need to consider the left part of the array. So I do not need to consider the left part of the array. After 21, I'll go to the middle of it, like 7 plus 14 by 2. So it's going to be the middle. Where is the middle? 56, right? 1, 2, 3, 1, 2, 3. So 56 is the middle again. 90 is greater, so this part gets discarded. Then my middle is 11 plus 14 by 2. So here 75. So 75 is also less than 90. So I come here. Now, so I discard from here. So my remaining part of the array is this one. So middle element is it 13th element itself, right? So you have one element in the array, sub array. So you have one element here. So it is itself the middle element. So you have found 90 here. Was it clear? Okay, so I'll show you the algorithm first. Let me, not this one. Okay, so here I have done the same thing. I have just taken an array, but first of all, you need to make sure the array is sorted, because we are taking advantage of the fact that the array is sorted here, right? Because we at 21, we know that the other elements are always going to be smaller than 21. So we can discard them. But if it was unsorted, so there was no guarantee that the elements cannot be present here. So see, 90 is here. So we cannot discard this part, right? So in case of binary search, it is really important that the array is sorted. Otherwise, you cannot take this decision to discard this part of the array. So first of all, we need a sorted array for this. So I have taken a sorted array. I have taken a key as input. And then what I'm doing is I'm taking a lower bound and I'm taking an upper bound. So in this case, so I'm trying to divide the array in half. So I'm taking a lower bound and an upper bound. I should have maintained a fresh copy of the array, but okay. So this is my lower bound. This is my lower bound. This 0 is my lower bound. And my upper bound is length of the array minus 1. So 14. So that's what I'm doing here. Length of the array minus 1. My lower bound is 0. Upper bound is 9 here in this case. The example that I have taken here. Now, so how long am I going to search? Until lower bound is less than equal to upper bound, because after upper bound is greater than, lower bound is greater than upper bound. So the array doesn't make sense, right? It does not represent any kind of array, right? So we are going to check until lower bound is less than equals upper bound. We are picking the middle index. We are finding the middle index. Middle index is lower bound plus upper bound divided by 2. So 0 plus 14 divided by 2 is 7. This is my middle index. So I'm checking if my element at the middle index is less than key. Element at the middle index is less than key. Less than key means not here. Sorry, this one was unsorted array. So middle element is here. So my element at the middle index is 21. So if it is less than key, that is my key was 90 here. So think in this case. So what am I going to do? I'm going to discard the left side of the array, right? My lower end bound was this and my upper bound was this. So if it is the element at the middle index is less than the key, then I need to discard this section. So my lower bound now becomes this one. 21 itself is not 90, so we can discard this as well, right? So my lower bound becomes this one. We are discarding this. So from lower bound to upper bound is the array that we are checking in. So my lower bound becomes mid. This was mid plus 1. So my lower bound becomes mid plus 1. And if it is greater than key, then if it is greater than key, so when I was trying to find 4, it was greater than the key. So I was discarding the right side. So my upper bound has to come here. So it's not equal. So upper bound doesn't need to be this one because we do not need to check this again. So my upper bound becomes mid minus 1. And if it is equal to, then yeah, we have already found it. So we do not need to check anymore. So we can just break it here. And if we have found it, so we are going printing it. And if not, then we are printing minus 1. So we have taken a default value as minus 1. So we have not found minus 1. Uh, Let me try searching something from here. So this is my array. And so suppose I'm searching for 8. 8 is found at index 2, 0, 1, 2. Suppose I'm searching for uh, 88. It's found at index 8. So this is working fine. So can you tell me what is the time complexity for binary search? Can you tell me the time complexity for binary search? Think it this way that we are, at every step we are discarding half of the array. The size of the array is reducing to half. So what will be the time complexity for this? Not n log n. Think a bit. It is actually log n, not n log n, log n. Yes. So why is it log n? Because at every step, we are discarding half of the array. So half of the array is gone now. So at first, the length of the array was n, then it became n by 2, then it became n by 4. So it becomes, at the end of it, it becomes n by 2 to the power something that gives me 1. Like it, at last, we have only one element. So at the worst case scenario, that will be the last element. So in that case, 2 to the power x is my n. So x becomes log base 2n, isn't it? So this will be my worst case time complexity. So best can be, we can just find it at the first search itself. Like if it is the middle element, then we found it in one iteration. So worst case and average case for a binary search is O of log n. So for linear search and binary search, can you tell me the space complexity? Space complexity for linear search and binary search? It's really simple. Give it a try. So space complexity is O of 1 actually. Why O of 1? Because if we are not considering this length of the array because it was already given, so my extra space that we are taking for searching is constant space. We are not taking any space at all, right? So it's constant space. So O of 1 in both the cases because we are not maintaining some kind of array or anything. So it's taking constant space. So both the cases for binary search and for linear search, we are taking O of 1 space. So that was binary search. Binary search works only for sorted arrays because if it's not sorted, we cannot take advantage of the fact, right? Because when it is sorted, we can know that if the middle element is greater than the target element, then it lies on this side of the array. So we are discarding. In case of unsorted, we cannot do that. So being sorted is really important for binary search. So what it does is divides the array into two sub-arrays, checks the middle element if it is the equal to key. If it is not, then it discards one of the sub-arrays that is relevant. So in this case, we are for finding 90, we are discarding this part of the array. And then we are going to perform the same thing on the subarray that we kept, this one. So we are going to perform the same thing on this subarray. Okay, so the worst, sorry, this one is going to be log n. I'll just change it. uh, the time complexity is log n and space complexity is O of 1. So let's try a very simple question that if you are given a non-negative integer, that you are given a non-negative integer n and you need to find the square root of it. Not square root exactly, but the floor of the square root. So if it is suppose 10, then the square root comes out to be something like 3.16 or something. So you have to return me 3. So the question is, given a non-negative integer n, find a number r such that r star r equals n and round down to the nearest integer, but you are not allowed to use the math.sqrt function. You have to find some kind of other way and try to do it in log n time complexity. Can you do it? Can you try? You can maybe unmute and say if you want to. Okay, so I'll just explain the code here. So suppose I have a number n, like I have just taken 1000 here, but you can take anything. So think of it as a sorted array because, let me clear the page. So think of this as a sorted array, like you are trying to find for maybe 1000. So you're trying to find the square root of 1000. So the square root of 1000 is going to lie between 0 and 1000, right? It's never going to be greater than 1000. So you can think of this thing as a sorted array, like the number line as a sorted array, 0, 1, 2, then 3, then 4 till 1000. So this, think of this as something as sorted array. And what are you trying to find? You are trying to find an R. You are trying to find an R that is that when squared gives you 1000. So R square gives you 1000. Not exactly R square, but the floor of it. So think of it as finding a floor in an array. So what do I mean by floor in an array? So suppose you have an array like this, like 2, 7, 9, 100, 200. So this is your array. Suppose think this is your array and you are trying to find uh suppose 20. So 20 is not in this array. So in my case, I'm saying that return me the largest such element that is smaller than 20. Largest such element that is smaller than 20. The largest such element smaller than 20 will be 9 because nothing can be larger than that because after that 100 is greater than 20. So we are trying to find the floor. We are trying to find the floor of 20 in this array. We are trying to find the floor of 20 in this array. So it is 9 here. So here in this case, we are trying to do something similar. So if it comes out to be something like, so if root of n comes out to be something like 4 point something, 4.167 suppose. So in that case, I'm going to pick 4 as my answer. So here I have the array. Think of this as the array, the number line as the array from 0 to 1000. And I'm trying to find the square root of 1000. So some value that r square gives me not equal to 1000, but rather less than 1000, but that will be the greatest value of r in this case. So not 4 here, it's going to be 31 point something, so 31. So what I'm trying to do in this code is, so my lower bound is L and upper bound is U, so 0 to N. So the square root can never be greater than that greater than 1000. So this is my lower bound and this is my upper bound. And my middle element, so I'm checking if the middle, number, so the middle element here will be the middle number. So if that is my square root of n, so I'm checking if that is my square root of n. So it's not an array. So this is going to be my number itself. Mid is going to be my number itself instead of being the index, just an index. So I'm checking if mid star mid is greater than n. So if this is greater than n, so what does that mean? So suppose you have something like here 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So let's take 10 as the n here. So let's not make it too complicated by taking 1000. So I have 10. So I'm going to the middle element. So my middle element is 5. This was my lower bound. This was my upper bound. So my middle element is 5 and 10. So I'm checking if 5 square, what does 5 square give me? 25. So 25 is greater than 10. So squaring this goes after 10, somewhere here, 25. So after that, if I take any number after 5, it's always going to give me greater than 25. I'm never going to get to 10. So 5 is not my value. 5 is not my answer, x, so that root of n. So 5 is not my x. So what I'm going to do is discard this part of the list. So discard these numbers. I'll check from here. So my answer lies somewhere around here. So I'm going to half of it again. It goes to 2 and it checks 2 square. 2 square is 4 now. Now 4 is less than 10. So if I take 1 or 0, it's always going to give me less than 10. I'm never going to get till 10. So I'm discarding this part of the numbers. So I have 2, 3, 4 now. This is my array now. This is my range concerned. So this is my L and this is my U. So the middle element will be 3. So the middle element will be 3. So 3 square is 9. Right? 3 square is 9. So 9 is less than 10. So I can discard 2 here. To see, I can discard 2 here. What I am doing is, mid square is less than n. So I am discarding 2 here and my L becomes this one. It was first 2. So my L becomes this one and my U is still 4. So between L and U, I get middle element is 3. 3 and 4 is there. So middle element is my 3. So after I get 3, what am I doing? I'm increasing this again, I think. Let me see. Yes. L plus 1. And U equals mid. Okay, so why am I returning U equals this thing? I need to explain. So suppose you have 3 and 4. My answer is actually square root of 10 is 3.16. So it lies somewhere around here, right? 3.16 lies somewhere around here. So this was my 3, that is L. This was my 3, that is L. This was my 4, that is U. And the middle element that I'm getting is 3. So I'm going to go to 4 here. And let me run it and see. This one. So 4 and 4. So my L becomes 4 now. L becomes 4. So we have already crossed this. L and U are equal, same. But L has already crossed this. That was my root, 3.16. But L and U are same. So I am checking till L becomes greater than U. So I can still check. So L and U are at 4 now. Both are 4. So L and U are both 4. So L is also 4 and U is also 4. So my mid value also becomes 4. Mid value also becomes 4. So what I'm doing when my mid value becomes 4, so mid value becomes 4 means 16. Now 16 is greater than 10. 16 becoming greater than 10 means this cannot be my answer. I need to check before that. So before that means U becomes 3. U becomes 3 and L was here, but U became 3. So my loop is going to end here because my upper bound is less than lower bound now. Now, but I have got the answer. My answer was 3. So what am I returning here? What is my answer? U is my answer. If you had taken L would have been at 4. L would have been at 4. But my answer is U because after this, it's going to go to the element before it. So 3.16, the element that is before 3.16. So that will be my U. So my answer will be U. So was I clear or do I need to explain it again? You can say if you couldn't understand, I will explain it again then. So this was simple binary search with just some modification. It was just simple binary search. What we are doing was we are taking the number line as our addition.
Can you explain the last part? Someone has
Yeah. All right. Okay. Explain the last part. So did you understand from where we got 3 and 4? So 3, this was my 3 and this was my 4. My lower bound had become 3 and my upper bound has become 4. Could you understand till this part? How my lower
Yes.
bound? Yes.
Just explain that part where both U and L became 4 and
Okay,
then
okay,
you
okay.
change.
Yes. So my actual answer, so my x that we are trying to find is something like 3.16, isn't it? It's something 3.16 that lies between these values, right? So it's something like 3, then 3.16, but we can never reach this part because that's not in our number line. So this is our condition. So this is L and this is U. Now I'm taking the mid value. So I'm taking floor here. So L plus U by 2, that is going to be my 7 by 2. So 3.5, that is 3. So I'm at 3 again. Yes, so I'm at 3. So when I'm at 3, 3 square is 9. 3 square is 9. So what do I do? When I have to discard my left part, I do mid equals L equals mid plus 1, right? L equals mid plus 1. Whenever I am discarding the left part, we are doing mid plus 1. So my mid plus 1, my mid was 3. Mid was 3. 3 and 4, mid is 3. So my L becomes mid plus 3, that is 3 plus 1. So 3 plus 1 is 4. So this is now my L. U has not changed. So L and U are both at 4 now. So when L and U are both at 4, so when L and U are both at 4, so my mid is now 4. Mid is 4. 4 plus 4 by 2. 4 plus 4 by 2, that is 4. So if my mid is 4, I'm checking here, mid square is greater than n or less than n. I'm checking these things. So 4 square is actually 16. So 4 square is 16, which is greater than 10. So we are crossing our n. That cannot happen. So we are trying to discard the right side. So when we are trying to discard the right side, what we do is u equals mid minus 1. u equals mid minus 1. So what was my u? U was 4. U was 4 and u becomes mid minus 1. So u becomes 4 minus 1. That is 3. So my u has come here now. So now my u is here and my L is here. So my loop should break because upper bound can never be less than lower bound. So my loop is breaking here. So I should have got my answer. And what is my answer? U is my answer. L cannot be my answer because U, only U can go before this. Like, right? For 3.6, I need something that is before 3.6. I do not need 4 here. I need 3 here. So U is my answer. I'm taking U as the answer here. Was it clear?
Yes, thanks.
Okay, so I have added links for some similar questions. Like these are really simple questions related to binary search. You just need this simple binary search algorithm and just need to tweak it a little bit. Like in this case, I'm returning U. So this was my answer here. Instead of taking some other value, index position value, I'm returning U here. So you just need to tweak it a little bit. Just change it a little bit. So these questions are quite simple. Just give them a try. I will give the PDF later. By tomorrow, I'll try to give the PDF and try to add some resources as well. So the questions, so binary search is actually really important. It's used in a lot of, you will find it's used in a lot of things like competitive programming and all. So it's simple and easy. So, oh, okay, I forgot the visualizer. All right, let me show the visualizer as well. So let's try to find a binary search for 205. So this is my array. This is my sorted array. So from index 0 to index 31, and I'm trying to find 205. So let's start. This is my lower bound and this is my upper bound. This is going to be my middle element. I'm checking, is it greater than 205? Okay, so I'm discarding this part of the array. Now this is my array. So I'm checking the middle again. So you can see that at each iteration, we are discarding half of the array. So you can see that we found. So if you're trying to find something that's not there, for example, 300, let me increase the animation speed. So at each iteration, we are discarding half of the array. Now, you can see that this was the upper bound and this was the lower bound. So it has crossed. So we are stopping here, right? So because we are discarding half of the array, we are getting log n time complexity. So in case of large data, for example, 10 to the power, suppose you are searching for 10 to the power 9 elements are there in the array. In linear search, it would have taken 10 to the power 9. 10 to the power 9. It would have to do 10 to the power 9 operations. But in case of binary search, you will just have to do log of 10 to the power n. That's definitely a very good algorithm. Like it's a much better algorithm than linear search. And jump search, interpolation search is also similar to this. Like it's an improvement over binary search. So jump search is also like that. Intervals, it's called an interval search because we are searching in an interval. Here we are taking this part, like for taking half of it. So we are searching in intervals. We are changing the range of the intervals and then we are checking. So I hope I was clear. You can ask me anything if you couldn't understand any part of it. So if you do not have any questions, then that's it from my side. I will send the PDF, but try to send it by tomorrow. And check out the questions. Those are quite simple. You'll be able to do them. I believe if you if you're facing any kind of problem, you can ask in the group as well.